the slope of the lines. Now, let's do the analysis a little bit, like go through more analysis and see how the voltage and the current waveforms look like. So instead of having two switches, what we can do was basically like similar to what we have in the buck-boost converter. We can just replace this one with a diode, right? So I'm just gonna remove this because this is like what we use to model this, but this is usually how it is shaped. And so this is gonna basically be working in the same way that we already saw. When the voltage here, when this switch is on, when the switch is closed, then the current wants to be released here, but it's going to be blocked by this diode. Okay? And when this switch is now opened, the current, it's going to release itself through here. Right, so this is going to be exactly similar to buck-boost converter. Now we can make this a little bit even better, because one of the things that we had to remember about buck-boost converter is that the polarity of output voltage is always opposite of the input voltage. Now what we can do is basically change the polarity of the secondary winding of the transformer, and now we can change the polarity of the diode. And if that's the case, if I just like show the load here, now with this configuration we would have the same polarity in the input and output. Okay, and we have only one switch and one diode, right? And now we can also, one other thing that is usually done is that this is like, let's say this is a MOSFET that we use here, right? In this case, it's a little bit more challenging to drive this MOSFET, but one thing we can do is basically move this MOSFET here. Where source is grounded. In this case, it is easier to drive this MOSFET, and it serves the same purpose. You just basically use this switch to have the current in the primary and store energy in the magnetizing inductance of the isolation transformer or coupled inductor. And then when you turn this one off, it basically cuts the current in the primary, and the energy stored in the coupled inductor releases itself in the secondary side. Okay, so this is how basically the big picture of the flyback converter. Now let's see a little bit more about the waveforms and other modes of operation of isolation flyback converter. So I mentioned about this relationship between L1 and L2, and I wanted to find the relationship between VO and Vin, but I think it's going to be easier to do it with the waveform. So let's actually draw the waveforms first, and we derive the relationship between output voltage and input voltage after that. So just wanted to show you again one more time that the way this is modeled is usually with a magnetizing inductance like this. And here I assume that we have a 1-to-1 turns ratio, but this can be 1 to n or n1 to n2. So that's actually going to have an impact on the output voltage. And here the energy is stored in the air gap and in the core of the coupled inductor. We also have some leakage inductance, which is one of the disadvantages of this this converter, but we're going to go through that a little bit later. And as I said, I wanted to draw the waveform, so let's do this together. So let's look at the VL, which is basically the voltage across here, across this. If I consider this the magnetizing inductance, I want to do the VL. We saw that this is like, again, very similar to buck boost. We saw that the volt-second balance is basically true for the buck boost converter. So we basically, for the same reason, it's gonna be valid for the flyback converter. So now let's see what's the voltage on the on the magnetizing inductance on the at the time that S1 is on. In that case, it's just going to be V in, right? So when this is closed, the voltage across this inductor, it's going to be V in or V1, right? When this is opened, so this was when it's closed, it's going to be V on. When this is open, so the turns ratio relationship between voltage on the primary and secondary is always valid. So like V1 over V2, it's going to be N1 over N2, right? So we have the output voltage on this side, VO, and this diode is going to conduct. So this voltage is going to be VO. And if the turns ratio is 1 over N, the voltage that gets transferred to this side, it's going to be VO over N. It's going to be actually negative VO over N. So this was V in, sorry. And this is going to be negative VO over N. Then the reason for negative is because of this change of the polarity here. So, and again, like I'm doing a bad job in scaling this, right? If you want to have the volt-second balance, then this is T, this is dt. Okay, so we can just write down V in times dt, which is this area, has to be equal to this area, which is VO over N times 1 minus D times T. T cancels out. So VO over V in, it's going to be N times D over 1 minus D.